Welcome. Thank you for coming. I'm Patrick Redmond. My collaborator on this project, Jonathan Castello, unfortunately couldn't make it. Today, I'm going to talk about a software design pattern called ECS and what we learned about how it enables concurrency. ECS is a software design pattern that was named around the year 2000. It has been widely used in video game development ever since, especially open world games with a variety of interacting game objects. ECS has been of interest to developers because it facilitates a flexible and high-level approach to programming, as well as providing low-level control over tight frame rendering budgets. ECS programs are also inherently concurrent, whether or not a given implementation employs parallelism. Writing a program in the ECS pattern is an extreme exercise in problem decomposition. You break things down into atoms of state and interaction that can be recombined to model some domain. Programming in this way might even be its own paradigm. So why study the ECS pattern? Well, it's been in use for at least 25 years, but has received little to no formal study. There's no semantics that captures what the common essence among the various ECS frameworks might be. There's no clear description of what kinds of concurrency are available to be expressed, parallelized, and relied upon to be deterministic. And there's no conversation between academics and practitioners about the many interesting problems of implementing the pattern. As Sriram suggests, PL researchers may act as natural scientists. We can model software development practices found in the wild. We can analyze our models, and uniquely, we can bring what we learned back to that wild setting to improve it. We took a look at several ECS frameworks and found that there's a delicious half-eaten sandwich of concurrency being left on the proverbial table. We designed Core ECS, a formal semantics of the ECS pattern, with a flexible scheduling notion. We used Core ECS to state precisely when concurrency in the ECS programs is going to be deterministic, and we analyzed the real-world ECS frameworks that informed our design and found that they restrict concurrency far more than required to ensure determinism. In this talk, I will give a sense of each of these results. So the acronym ECS stands for Entity Component System. In the next section, I'll go over each of these parts of the pattern to explain how an ECS program is constructed. Along the way, I'm going to introduce an example toy physics simulation, which is very old and always used to explain ECS. So let's first place the spaceship and the asteroids on a number line. The first part of the entity component system pattern is entities. Entities are opaque identifiers for program objects. And so in this example, a set of numbers is enough to represent the entities. But it's important to recognize that the spaceship and the asteroid aren't a spaceship and an asteroid. They're just untyped entities. The second part of the ECS pattern is components. Components describe entities, since entities have no data fields of their own. Components can be attached to or detached from entities at any time. Here I've drawn some components attached to each of our entities. Both of our entities have a position component and a draw component, and the asteroid doesn't have a velocity component, the ship does. When we want to move the ship, we update its position component. This is because the position component is used to decide where to draw the ship on the number line, just as the draw component determines what to draw there. Entities and components together comprise the whole runtime state of an ECS program. This soup of entities and components can be conceptually organized as a two-level partial mapping, indexed first by component label and next by entity. Here I've organized the component values down into just such a mapping. This is how Core ECS models ECS program state. A component label paired with an entity is like a memory address in this scenario. I'll keep the state mapping on the slides for a little bit longer, but only show the position and the velocity submaps. All right, so the third part of ECS stands for system. Systems define the behavior of an ECS program by specifying how entities and their components are going to change over time. To move the ship's position by its velocity, we're going to need to define an inertia system. Systems declare their input as a query against the entity component soup. Here I've shown the query for the inertia system, which matches entities that include a position component and also include velocity. Some systems may also exclude entities having a certain component, or obtain multiple entities by crossing the results of two queries. Systems are the part of an ECS program that attach components to entities, detach components, create new entities, or delete entities. We call those activities mutations. I've shown here the mutation function for the inertia system as specified in Core ECS. It adds an entity's velocity into its position, making it move. After the inertia system's mutation function is applied, the ship's position component is updated in the state mapping. Now the ship and the asteroid occupy the same position. So for our example, we'll have a collision system to handle this situation. The collision systems query crosses entities with both a position and a velocity component against entities having position but not velocity. That is, we're only modeling collisions between a moving and a stationary entity. The mutation function for this system is a little too complex to show on the slides, but it's going to delete the moving entity. It's going to give half of its velocity to the stationary entity, kicking it off in the direction of the moving entity. And it's going to create a new entity going the other direction. I don't know if my thumb's going the right way. That means the ship is going to be gone, and there will be a new asteroid. So finally, after we apply the inertia system once more, we're going to see that these rocks are moving as ejecta away from the collision. That's just our example program. But since we have two systems in this example that mutate state, you might be wondering about when exactly each system runs. So that's what we're going to focus on. So what exactly is an ECS program? If you stop with just that acronym, an ECS program consists of some component data types, some systems that query to mutate state, and some initial state that gets things rolling. But that's incomplete. It doesn't address how each system actually executes by itself, and it doesn't address how systems execute with respect to each other and what order they're going to execute. So in our formalism, an ECS program is an explicit schedule of systems. A core ECS schedule defines when systems run with respect to each other and exactly where in the program concurrency is going to occur. The schedule given at the bottom of this slide is the schedule for the toy physics example we just went over. It says that the collision system is going to run sequentially first, and then after it's done, the inertia system will run concurrently with itself. All right, so where is that concurrency? It's going to exist wherever the conc and the parbars schedule forms are used. An ECS program exhibits concurrency among systems when parbars is used to compose two subschedules, and it exhibits concurrency within a system that is introduced using that conc form. Mutations generated by systems under these forms are reorderable according to certain rules. And that relaxed ordering is what models scheduler non-determinism that would exist in a real parallel program. So given that we know where non-determinism may arise, we should define determinism. Well, in our formalism, determinism is just that a program is going to be deterministic if it always produces the same result, irrespective of the possible scrambling of the order of mutations under those two schedule forms. So finally, we'll want some way to ensure determinism, and to do that, we're going to have to restrict the use of parbar and conc somehow. So to explore that, let's revisit the toy physics example briefly. Here we have a rightward moving spaceship and a leftward moving ghost and a stationary asteroid. Both objects reach the stationary object after the inertia system. And since there are two entity pairs now, consisting of a moving object and also a stationary object, there are two potential collisions. How should the collision system be run to ensure determinism? Since this question relates to the ordering of systems, to answer it, we need to examine the ECS program schedule. We'll explore two resolutions, two schedules. First, I'll use the schedule shown earlier, in which the collision system runs sequentially before the inertia system. Since our schedule runs the collision system sequentially over the pairs of entities, only one collision occurs. This is because after the first collision, the rock is going to have a velocity component, and so it's no longer eligible for the second collision. Due to an arbitrary deterministic ordering of those entity pairs, we'll choose that the ship is going to collide today. That choice is not a result of concurrency. That's just an artifact of ordering the entity pairs. In any case, after the collision is done, the ghost didn't collide, so it continues unimpeded. And our choice of schedule is what ensured the deterministic result. So to contrast that, here's how the scenario resolves with a schedule where the collision system runs concurrently with itself. That means that both potential collisions are going to occur. More mutations are generated, and these mutations are all mutually reorderable because of the conc schedule form. So we have a problem. Both collisions mutate the rock number 2. That's the one that was in the very first line. Since only one of those mutation orderings can actually occur at runtime, and we don't know which one, the result is a loss right and therefore non-determinism. So now that we've seen how it can go wrong, we'll want clear rules for when concurrent mutations are going to be deterministic. Simplifying the rules from our paper quite a bit, we have that concurrent rights are deterministic when they're disjoint. And it's not news that only disjoint rights commute, but proof that this old news transfers into the new context of the ECS pattern, that's new. And it's the presence of the formal model of the ECS pattern that made obtaining the result possible, even if it's really obvious in hindsight. And now that we know that much of the half-eaten sandwich of concurrency is actually deterministic, we want to use it. So let's look at some existing real-world ECS frameworks. I looked at 5 frameworks to see how concurrency is expressed and executed. Not all of them are actually multi-threaded and et cetera, so we're going to talk about the first 3. And it turns out that of these first 3, Bevy, Specs, and Flex, it turns out that all 3 of these only distinguish several kinds of mutations and only allow some of them to be used concurrently. So the first kind of mutation that these 3 frameworks all distinguish is called an in-place update, exemplified here by attaching a component to an entity that already has that component. The second kind of mutation is called a structure change by the author of Flex, actually. Attaching a new component to an entity, as shown here, and detaching a component from an entity are both structure changes. And the last kind of change is a lifecycle change, which includes creating an entity or deleting an entity. The differences between these types of mutations starts with the ECS frameworks providing distinct APIs for each. And it ends with the frameworks treating the mutations completely differently from each other. Only in-place updates can be expressed in a concurrent context and also execute in parallel. None of the 3 frameworks execute structure changes or lifecycle changes in parallel. Those are saved to a buffer and serialized to be applied sequentially between system executions. In Core ECS, these changes are all just attach and detach operations because it's a semantics, not an implementation. That the ECS frameworks treat them differently exposes a leaky abstraction. The frameworks make use of global mutable state that requires mutual exclusion to safely modify. They might be prioritizing efficient data parallel throughput for large-scale simulation-style ECS programs where entities mostly experience in-place updates, but we didn't investigate this. However, if ECS frameworks were to lift these constraints, it might provide us with an ECS pattern applicable to general-purpose concurrent programming tasks. You'll have to see our paper for the details. Our formalism, the rules for safe schedule construction, and our exploration of existing frameworks are all there. I think that the problem of how to express concurrent programs that are obviously correct and easy to parallelize is still unsolved. While the ECS pattern itself doesn't solve the problem, it is a location in the space that the PL community has yet to investigate fully. That's all. Thank you for listening today. Alrighty.